that I received so far already. I've gotten one. I got one from Kathy, I got one from Matt, and I got one from Ariel, and so I'm going to try and kind of sequentially to go through those videos. You see some cool fluid phenomena that's just super exciting. Go ahead and send them to me. So before we actually get started with class today, we're going to watch Ariel's video. So let's take a look at this. This was related to what we were talking about with a little bit in terms of pressure and temperature.
There were more surprises ahead. In the 1930s, another strange phenomenon was observed at even lower temperatures. This rapidly evaporating liquid helium cools until at 2 degrees above absolute zero, a dramatic transformation takes place.
Suddenly, you see that the bubbling stops, and that the surface of the liquid helium is completely still. The temperature is actually being lowered even further now, but nothing particularly is happening. Well, this is really one of the great phenomena in 20th century physics.
The liquid helium had turned into a superfluid, which displays some really odd properties.
Here I have a beaker with an unglazed ceramic bottom of ultrafine porosity.
Ordinarily, this container with tiny pores can hold liquid helium. But the moment the helium turns superfluid, it leaks through.
We call this kind of flow a superflow.
Superfluid helium can do things we might have believed impossible. It appears to defy gravity. A thin film can climb walls and escape its container. This is because a superfluid has zero viscosity. It can even produce a frictionless fountain, one that never stops flowing. Superfluidity and superconductivity were baffling concepts for scientists. New radical theories were needed to explain them.
So that's where we're going to start. In case you were not aware of the song that was playing when we came in, that was Under Pressure by Queen, and that's kind of to orient you to the subject matter today, which is going to be pressure. But before we get into pressure, I've got one more video to show you on something called a vortex cannon, which is also related directly to fluid mechanics and some of the things we're going to be talking about.
According to legend, a really good blast of air should be able to bring down a house of straw.
This is a guy who built a vortex cannon.
Generated vortex ring.
And talking
This is
about
the
the
gas.
fluid mechanics of air and vortex ring
It's the
creation.
first time it's ever been fired, and with 150 litres of one of the world's most explosive gas mixers in there, I'm not even sure that this is really a safe place to stand.
Seems about right. I'm going to need these, I reckon.
Okay.
3, 2, 1. Oh, yes!
Call me hopeful,
Wow, see,
but there
someone's
is
really
definitely
excited about
something
fluid
there.
mechanics. Pretty good.
But was it a vortex ring? Filmed at 1300 frames per second, there is no doubt. But the ring you can see is not a smoke ring. It's formed by the pressure drop within the vortex, condensing the water out of the damp air above the lake.
Right, since we're talking about pressure today, and in pressure drop, we'll get into that later in the
Bring on the
semester.
sticks and bricks.
You'll actually be able to calculate that pressure drop across a ring like that.
3, 2, 1. What? Yes!
Okay, so these houses are obviously put together by like.
Well, it makes mincemeat of a house of sticks. Bring on the bricks.
I would expect.
Even in
You
fairy
know, as
stories,
engineers,
they
you
couldn't
put
get a
together
blast of air to knock down a house of bricks.
house than this, but
We're heading into the
for
world of
his
the unknown a
purposes,
little
it'll
bit.
work.
So we've got to experiment. We're going to try changing the elevation on it, changing the gas mix in there, see if we get a perfect gas mix. So that's just the right amount of molecules of acetylene reacting with just the amount of molecules of oxygen in the air. So there's no passengers in there, it's got to be all explosion. Let's see how that goes.
Oh God, the suspense.
Three, two, one. Hey! Yes!
Okay. So there you're able to see the power of a vortex cannon. Now, you know, I like to play with stuff, so I don't necessarily have, you know, his high tech, I think it was propane powered, something or other like that, vortex cannon. But, you know, I can build a structure that's easily as good as what he did with his wood and his bricks, right? It's about the same stability. But our vortex cannon, on the other hand, is really highly sophisticated. You know, it's got all those wires and propane and all that stuff in there. So, I'm going to need somebody to volunteer to smack the sides of this really, really hard. Who wants to volunteer? Nobody? Danny, you want to do it? Yeah? Okay, I'm going to hold the vortex cannon right here, like this, and you're going to smack both sides of it really hard. Yeah, but you have to stay out of the way. Yeah, like that. So smack it really hard. Yeah. Yep. Perfect. Uh-oh. Maybe we didn't aim it right. Go for it. Stick your part in the way. Okay, so maybe it doesn't need that much. Let me see if I can get it to work. So you just hold it and go. Oh God, our vortex cannon. Time out. We're gonna need another vortex cannon. I got it back. So it like all this.
Yeah.
Why don't we just two people just use a chair?
Okay, so this has worked every other semester ever. Now vortex cannon's dead. Okay.
Wow.
So let's see if we can get this to work. So if you hold it like this.
Oh, there you go.
It's not close. You just gotta. Come on. There it is. So they actually do work. This we're gonna have to retire this one. It's completely dead. Daniel's a little too strong for us. So thank you for your assistance. After that.
Incredible!
Oh yes, it is very. All right. So in terms of housekeeping for the day. Intros, thank you very much. I enjoyed reading everything about you that you gave me. It's really good to learn about everything, you know, why you guys are in engineering, what you're passionate about. I really do appreciate those intros. I do have a correction from last time. I don't know what I was thinking, but quicksand is definitely a shear thinning fluid, right? Otherwise it wouldn't be quicksand and it wouldn't be dangerous, right? So if you're in quicksand and you put shear on it, that's when it liquefies and becomes thin and you sink down into the bottom. So make sure to make that correction in your notes from last time. And then the viscosity lab is going to be Thursday. Fluid song from the box Zoom is due now. Homework number 2 is going to be due on Thursday, and homework number 3 is the following Thursday after that. And then please read section 2.1 through 2.7 in your textbook for next class. All right, so our lesson objectives are today, by the end of the class, you will be able to complete all 3 of those lesson objectives. And those 3 lesson objectives are calculate the pressure at various locations in a fluid at rest, calculate the pressure at various locations in a fluid at rest when variations in gamma occur. And we talked about gamma last time. That's a specific weight of the fluid. So we're talking about fluids that have different specific weights. And then explain hydrostatic pressure distribution and variations in head. We'll talk about what that is with location in a fluid at rest. So back to the first day, right? We had our squirt gun, right? Today, You know, we were talking about what the different parts of this are going to be by the end of the semester. You'll know exactly how to calculate trajectories and everything else. Today is this part, right? Talking about pressure and how that's going to relate to everything from that point on. So let's start off with something called the bulk modulus of a fluid. Does that sound like a familiar term you may have heard before, Jeff? Modulus? Yeah, modulus of elasticity. Yeah, elasticity. So the bulk modulus is essentially the modulus of elasticity for a fluid. Now the question is, what could this possibly be for a fluid? Right? What did the modulus of elasticity diagram look like for, say, steel or aluminum? Anybody remember what that looked like? Right, you had like an elastic region. I'm just going to draw this up here real quick, but I'm going to erase it again. But it looked something like this, where it came up, right? You had like an elastic region, then it kind of bent, and then eventually it kind of failed off like that. Right? That was your modulus of elasticity for a like steel, aluminum type of thing. So what could our modulus elasticity be for a fluid? What things do we have for fluid? I mean, it's not going to hold any load. How could we define something like a bulk modulus? Tension? Yeah, maybe. Like we talked about surface tension? Yeah. That could be a way to do it. Let's, Jabari. Has something to do with the viscosity? Not quite. So think about, what did we say you couldn't do with the fluid? Compress it, right? So that's exactly what it's related to, is compression of the fluid.
It's fine, isn't it?
So, it essentially represents how easily the volume of a fluid be changed by pressure. So bulk modulus is the same as materials, EV, and it's essentially written as the negative change in pressure dP divided by change in volume with respect to volume. And it's usually in pounds per square inch or in newtons per square meter. Let's think back to last time, right? You had that square inch on your hand, right? If you were following along, you drew a square inch on your hand. How much pressure did we have on that square inch? 14.7 psi, right? That's 14.7 pounds per square inch. Perfect. So now, let's think about what kind of psi might you need to actually change the volume of water by 1%. So if you wanted to compress water by 1%, how much pressure would you need to pull that off? Any ideas? 1 Newton per meter squared? Not quite. It's going to be quite a bit more than 1 Newton per meter squared. It's going to be many, many compress water by 1% is 3,100 psi. Who's got a calculator? You got one, Josh. You want to tell me how many atmospheres that is? 11 atmospheres? 211 atmospheres. That is pretty serious pressure that you need to change the volume of water. So does this validate an assumption we made in the previous lesson? Maybe? What assumption did we make about fluids? They're not compressible, right? And does that hold true in all the pressure ranges that we're generally going to see? I would say so. I mean, 211 atmospheres, we're not going to see that anytime soon in anything that we ever calculate. So this validates the assumption, for one, that our fluid is incompressible. All right, so on to pressure in the fluid itself. So what is pressure in the fluid? Right? Can we define that as a normal force per unit area? We're going to look at two distinct cases for fluids because we have either a fluid at rest, that's the first case. So fluid at rest, that's what we're going to be talking about for the lesson today. That means the acceleration is equal to 0. And this is where we're going to start. And then the second case is if you have fluid in motion. Right? And that's where your acceleration in the fluid is not equal to 0. And we're going to talk about that in detail as we move through the semester. So we have to get a grasp on hydrostatics, which is fluids not moving first, and then we'll go on to how fluids behave when they're moving, and we'll learn some of the equations for that later on in the semester. So in a fluid, there are several forces, right? Jabari mentioned one of them just a few minutes ago, right? He said surface tension, right? So we've got forces that act in a fluid. He said, oh, sorry, Josh, you said surface tension. Excuse me. You said viscosity. Okay. Sorry, thanks for the correction. So thank you, Josh. I'll come back to you, Jabari. We'll get an answer out of you. So forces on a fluid, there's all sorts of different forces acting on the fluid, and one of the first ones that we're going to list here is something called a surface force, right? And that would be surface force is due to pressure that can be acting on the fluid. Surface tension can come into that, and then the other one, right, that we talked about probably quite a bit in mechanics, are body forces that act on a fluid. And those would be due to weight, and they're caused by gravity. neglect are such things as magnetic forces acting on a body, because they do exist, but in our discussion of pressure, those aren't going to affect it specifically. So what we're going to look at here is we're going to look at fluid in some type of container. And we're going to call this differential fluid element. And we're going to look at all the different portions of the pressure forces that are acting on it. So this is going to be our differential element. We're going to come back to that specifically in the PowerPoint. So the question I'm going to pose to you now is, how does pressure in a fluid, and let's take this differential element for example, let's say you're looking at that differential element sitting in that fluid, how does pressure vary depending on orientation? Think about that for 30 seconds. Does it vary in the x direction, in the y direction, in the z direction?
Maybe in all directions.
What's that?
Maybe it's in all directions.
In all directions? Does it vary or not?
I don't think so.
You don't think it varies? Why not?
Because it's around a fluid and it's homogeneous. So homogeneous.
Right, yeah. The fluid we're talking about in this differential element is indeed homogeneous.
So then it shouldn't vary.
It shouldn't vary depending on which direction you're coming from, if you're coming from the bottom or the side. Well, that's exactly correct, Ariel. So the point here is, how does pressure vary depending on orientation? And the answer is, it does not vary. Make sure you got that in your notes. I hear all the pens clicking, so that's wonderful. Camilla.
Is that for both fluid at rest and moving?
This is only for a fluid at rest. So a fluid in motion is going to have different forces on it. It could have varying pressures, and we'll talk about that when we get to the Bernoulli equation later. So pressure does not vary depending on the orientation, and one of our very famous aqua heroes actually came up with this, and it was Pascal. And this was from, he lived from 1623 to 1662. And it's Pascal's law of hydrostatics, essentially. And where is Pascal? I know he's hiding out here somewhere. There he is. Here's Pascal. Right, so he is responsible for this whole theory of hydrostatics. He's right up here next to where you could be someday. So, Pascal's law of hydrostatics is that pressure in a fluid is independent got a container of sorts, right, like a big vessel. We put our differential element in it down here. That means that our pressure, call it pressure in the y direction, and our pressure from the z direction here, and our pressure in the y is going to be equal to our pressure in the z. Only problem with this drawing is you don't have a fluid in there yet. So now we do, and it works out there. And let's get the PowerPoint up and show you some examples. Of specifically what I'm talking about. So this is a slide back from last time. Talking about the vapor pressure again, so you can take a look at that separately. But here is that pressure at a point. So we've got this arbitrary fluid wedge. We've got no shearing stresses, right? Because they're not moving. Only external forces due to pressure and weight. Right? So that's our differential element from drawing up on the board. And so some of the forces in the y and some of the forces in the z here are only due to the pressure and due to the weight on that fluid. And so this equation, once you start simplifying, plugging in your geometrical relationships here, a lot of those pieces fall out. And then if you take the top equations and divide both sides by dx to z, and the second equation you divide both sides by the same thing, except dx dy, and then you take the limit as the size of your element gets smaller and smaller, you essentially see that your pressure in the y, your pressure in the z, and pressure in the x, this is defined as pressure in the s for this example from the textbook, that those essentially all become the same and validate Pascal's law of hydrostatics here, that pressure is independent of direction. All right. So let's talk about what happens, right, when pressure is associated with depth in a fluid. Right? Because we know now that pressure doesn't depend on orientation. Right? Okay. Any questions before we move on with that? No? Not too many teacher spaces, so we're good. The next question is, how does pressure in a fluid vary with the depth C in that fluid? Think about it. Who are my scuba divers out there? Yeah, I remember that from your intro. So they just get a weight of water. The weight of the water?
I mean, that would increase pressure on an object at a certain depth.
So the weight of the fluid above you
Correct.
is what creates the pressure as you move further down because there's more weight of that fluid above you. So do you want to add something to that, Thomas? Well, it's definitely related to the density of the fluid, right? How would you feel if you had to, lay in a bathtub at the bottom of a bathtub and there's a foot of water over you? You'd hardly even notice that, right? The mercury, on the other hand, is maybe, what, 13.5 times denser than water. Did you notice that if you were laying a foot of mercury? Maybe. You most certainly would. So, how does pressure vary with depth? The variation of the pressure, essentially, is dependent on the weight of the fluid above you, and the variation, as you can expect, is linear, right? Because as you're adding another increment of weight in that fluid, right, you're going to have a nice linear distribution. So at rest, in a fluid, at rest, pressure, the pressure gradient in a fluid in the vertical direction, I'm going to call that Z, depends only on gamma. What was gamma then? What was gamma? We talked about gamma for different fluids. You can phone a friend if you have to. The specific weight of a fluid. Yeah, thank you, Samantha. There's a specific weight of the fluid, right? And that's directly related to Ariel said pressure. That's the pressure, the density, right? Yeah, because like for water, the fluid that we talk about most often in this class, right? Its specific weight was 62.4 pounds per cubic foot. So that's analogous to if you have like a cubic foot, right? You pile a bunch of those up, that's a lot of weight that would be down on you if you were scuba diving, or we're in your mercury filled bathroom, which I highly don't recommend doing. Probably not a good idea.
I think I'd find that much lighter.
Yeah, you'd have trouble getting your hands on that much for sure. So the relationship here is that the change in pressure with respect to Z is directly related to your specific weight of the fluid, and I'll show you a couple examples of that. Oops, too far. Okay, so the forces essentially that you're going to have that are acting, yeah, Jason.
Why would it be a negative? Why is that negative?
Because as you're going down, right, pressure, yeah, that's okay. No, it's a good question. I mean, the first time you look at it, you don't think, oh, yeah, right. But as you're going down, pressure's got to increase. So, yeah, that should clear up your question there. So the fundamental equation for the change in pressure for forces at rest, the big overarching equation here is given by this. So you have this in your notes. I don't expect you to know this or go into this in detail. There's many that came before you that did this, and I just expect you to be able to use this equation and this relationship, which we will do by the end of the class. But I just wanted you to have this so you see where it comes from, where that's derived by, that the change in pressure is essentially just related to those forces. So we're going to have one more slide on forces, but here you can see that all of these actually cancel out, and that leaves this relationship right here, and that's your gamma, and that's directly related to how you move in that fluid. All right, so that ends the PowerPoint for today, but we'll have other things to look at here. This. continue on with pressure distribution. As we're moving down in a fluid. All right, so we're going to draw that same more or less fluid representation here with the bottom of that surface and surface of the fluid. Move that down a little bit. Probably do the same in your notes too, so you got enough room for this. I'm going to set our coordinate axes essentially as x, y, z. And let's say right, we're going to do the particle. Our particle is right there. We're going to look at the hydrostatic pressure distribution, how that changes from different locations. So let's say we got a depth C1, and then we've got another depth C2 from that point. So we'll have pressure at point 2 and a pressure at point 1. So if our particle there is moving around, depending on where it is in relation to this, it'll have different pressures. Actually, sorry, that's the wrong one. P1. Okay, so if our particle moves up from where it is now to that point, Z1, there's going to be a change in pressure. And if it moves up from there, even on further to Z2, as it, let's say, comes up in that fluid, what's going to happen to the pressure? Is it going to go up or down, Matt?
Down.
Down, right? Because you're rising, so there's going to be less weight of that fluid above that particle. Perfect. And one thing that we're going to talk about is this H term that's going to be Z2 minus Z1. And essentially here, we take the integral P2 to P1 to get our change in pressure UP that's going to be equal to minus gamma from Z2 to Z1. We're going to integrate over Z, right? If we pull that out, it essentially just becomes that P2 minus P1 is going to be equal to minus gamma Z2 minus Z1. So if we're looking at any changes in that pressure across there, right, that's all it's related to. And that means that at any given point, I can write this equation to look something like this. I can say pressure at P1, right, is going to be equal to gamma times H, right, which is the difference between Z2 and Z1, which is this piece right here. Right, I can just write it as that, plus pressure at point 2, and this is from page 42 in your book. And this essentially defines our hydrostatic pressure distribution. And P, our pressure, always varies linearly with depth. here's the key that you intuitively know, is that the pressure must increase to hold up the fluid above. We're going to erase our differential element here. We've got a couple more boards to put up here, and then we're going to go on to an example and see how that progresses. We've got two more things to put up here. One of them you're going to fondly remember is something we're going to call the container of doom. Some of the seniors still remember that, especially when we're talking about pressure and reviewing for the FE, but that's a different kind of pressure. So, yeah, we'll get those two boards up here, and then in terms of material delivery, that's essentially it for the day. I know it's a lot all at once, but then really you'll have your worksheets to practice on. So, pressure head is a different term to refer to pressure, and it's essentially the relation that H, right, that's your pressure head here, is equal to P1 minus P2 over gamma. So that's in this relationship here to show you that that H, your pressure head, is P1 minus P2 over gamma. And the idea is here, I'm going to draw a tube here. My tube is going to have an area that's 1 inch squared. So the area equals 1 square inch. That means that my pressure times area up here exposed to the atmosphere is 0. Okay? So if I fill this tube water, and the tube is 23.1 feet long, that means I'm going to have a weight of 10 pounds of water in there. And down here, my PA, pressure times area, is going to be 10 pounds per square inch. So that conversion here, and I want to make that absolutely clear, that 10 psi down here, 10 psi, is equal to the same as 23.1 feet of water. Right, so this right here, the 23.1 feet, that's an example of pressure head. Right? So think about, let's see, who's got a watch that says how many ATM your watch goes down to? Anybody? What's that? Yours just says feet? Yours says meters. Okay, who has one that says ATM? Anyone? Your watch, is it waterproof? Okay. My watch, I think it says, my watch is waterproof to 10 ATM. 10 ATM. So let's convert 10 ATM to feet of water, right? And then get the idea of what a pressure head is. So this is a pressure head, which is what we're talking about here. To get in the concept that you can say pressure as a linear distance of water that's sitting on top of you to make that pressure. So if my watch can go down to 10 ATM, 10 ATM, okay, what is that in terms of PSI? That's 14.7 PSI times 10, so that's 147 pounds per square inch. Does that really help me turn it into a conversion of any sort? How does that help me turn it into feet? Right. So we multiply this, right, by 23.1 feet per 10 PSI. Right, so then all that will cancel out. How many feet of water does that come out to be, Alice? 339. So 339 feet is how many feet I could go down underwater before my watch would totally explode on itself and stop working. Yeah, I probably would not want to do that anyway without having some diving training or something like that. But the other convenient thing here is, right, can you deduce from this how many feet of head and water are related to one atmosphere? This is going to be a number you're going to be very familiar with for the rest of the semester and the rest of your time here at FGCU annually.
I know that every 10 meters there's one atmosphere, so like 33.
Yep. Every 10 meters is one atmosphere, or every 33 feet. So 33 feet of water is equal to one atmosphere, right? You divide that out, drop that 10 atmosphere through that, and you get that relationship. So it's amazing thinking about the weight of the fluid, right? One whole atmosphere, right? From here all the way up to space. Like the 14.7, you've got it on your hand, right? That's one atmosphere. That's, I don't know, 60,000 feet of air sitting on top of you. You get the same effect by going down in the water, only 33 feet. Yeah. It's a pretty crazy real world example of pressure head and how that affects everything here on Earth. So, let's ask, let's see, who haven't I asked a question? Ian, you want to help us out? Fluids in the news, page 43. What does it say? This is related to giraffes and pressure. It's kind of weird, but
The entire thing?
go for it.
A giraffe's long neck allows it to graze up to 6 meters above the ground. It can also lower its head to drink at ground level. Thus, in the circulatory system, there is a significant hydrostatic pressure effect due to its elevation change. To maintain blood to its head throughout this change in elevation, the giraffe must maintain a relatively high blood pressure at heart level, approximately 2.5 times that in humans. To prevent rupture of blood vessels in the high pressure low leg regions, giraffes have a tight sheath of thick skin over their lower limbs, which acts like an elastic bandage in exactly the same way as due to the G-suits of fighter pilots. In addition, valves in the upper neck prevent backflow into the head when the giraffe lowers its head to the ground level. It is also thought that blood vessels in the giraffe's kidney have a special mechanism to prevent large changes in filtration rate when blood pressure increases or decreases in its head movement.
Right. Thank you, Ian. The reason I wanted to point that out is because a great way to imagine a giraffe's neck, right? If it's like grazing down on the ground, you know, you've got this huge neck on a giraffe and it's grazing down on the ground, right? There's some pressure there, but when it kicks back up, its heart has to overcome the weight of all that fluid that's like